Let me start sharing. Okay. So yesterday I gave a general overview of the topics that I'll try to cover. And today I'll try to describe some explicit calculations. But before I start, let me just make a few corrections. There is one question yesterday about the definition of the coupling constant in Liouville theory of GS in Liouville theory. I think probably Pablo asked this question.
Yes, thank you.
Okay. So the point is that the dilaton, I had said that the coupling goes to some finite value at infinity, but it's actually not true, because dilaton is like minus k times phi plus c, where phi is a Liouville direction. And k and c are constants. Okay, so these are constants. And k, of course, is determined by the central charge. K is adjusted so that the Liouville sector has central charge 25. So the string coupling, the conventional string coupling, is e to the dilaton. So that goes as equal to minus k phi plus c. So that means that this goes to 0 as phi goes to infinity. And this is in fact good, because if the coupling had been non-zero at infinity, then given that there are massless states, there's like the closed string tachyon here is a massless state, it will be very difficult to define S matrix, right? Because we know that in 2 dimensions there are infinite divergences as well as massless states. And it will be difficult to define an S matrix of massless states in 2 dimensions if there is a non-zero coupling constant. But the fact that the string coupling goes to 0 makes the theory free at infinity, and hence you can define asymptotic states and S matrix. So what GS is, okay, roughly, is this one, e to the c. Okay, it's some constant over here. Now, operationally, the way we define it is as follows. Okay. So if we look at the effective potential for the tachyon field, closed string tachyon. Okay, if we look at the V of effective, which is for the closed string tachyon versus the Liouville field. Okay, as alluding to yesterday, it has a shape like this. There is a wall. So this means that if you throw in a phi from infinity, then as far as the CFT is concerned, it will just come back to it will just get reflected back from the wall. And this is the correct picture for GS equal to 0. Okay, so this is for GS equal to 0. But it turns out that there is a non-zero amplitude for one incoming tachyon to split into 2 tachyons. And that amplitude is given as some constant GS times F omega 1, omega 2, omega 3, where say omega 1 is the energy of the incoming tachyon and omega 2 and omega 3 are the energies of the outgoing tachyon. Of course, we have energy conservation, so there are only 2 independent parameters. So F is a known function that can be computed from the Liouville theory. And this multiplicative constant defines GS. Okay, so in a sense, you define GS to be some constant that multiplies the 3-point function. Okay, so this defines GS. And once you define GS this way, okay, then by using bootstrap, you can determine all the 4-point functions and higher point functions, higher genus amplitudes, everything in terms of this GS. And you can also include calculate the instanton action in terms of this GS. And that's what this answer 1 over GS that I mentioned yesterday corresponds to. Okay. So GS is defined by this. Okay, roughly it's like e to the c, okay, the constant part of the exponential of the constant part of the dilaton. But operationally, it's the coefficient of the 3-point function that appears in the 3-point function.
I see. And this C depends on can it be chosen so that GS is small?
Yes, it can be. So GS is arbitrary parameter here.
Mm-hmm.
So GS is a
Depends just
continuous
on,
parameter that you can adjust, just like in normal critical string theory.
right. Okay, that helps a lot. Because I was a bit puzzled still how you could do wordsheet theory in a strongly couple otherwise. It makes sense. Thank you very much.
Okay, thank you. Okay, any other question on this? Okay, so another correction I have to make, okay, which I missed out yesterday, is that I wrote down the expression for the normalization constant, if you remember, n, and this is in fact what we are going to calculate. I wrote it as exponential of the annulus amplitude. Okay, and I'll write down the expression for this again. But it's actually I times this. So this I is a factor that appears in all string amplitude. It's not special to D-instanton or anything. Okay, and roughly you can think of that when you try to relate the S matrix to analytic continuous of Euclidean Green's function in momentum space, okay, there is a factor of I. Okay, and that's essentially to have to do with the fact that when you go from the Euclidean to Lorentzian space, this e to the minus s becomes e to the I times s, right? So when you expand it out, there is a factor of I. So that's this I. Okay, it's a standard kinematic factor that appears in all string amplitudes. Okay? And the definition of n includes this. Okay, so for example, the expression for that leading order amplitude A0 that I wrote down contains this I. So this is I, let me diagrammatically, it's the exponential of this annulus. Okay. And I wrote down explicitly the expression for the annulus. Okay, so A, okay, we'll see today in more detail how this arises, at least part of it. Trace, sorry, it's the answer that I wrote down was e to the 2 pi t minus 1. Okay, but today we are going to start with a more general definition. So we'll start with a more general definition that is valid for all string theories. Okay, at least all bosonic string theories. For superstrings, there is slight difference. And that is that the annulus amplitude is integral 0 to infinity dt over 2t times trace e to the minus 2 pi TL0. Times minus 1 to the f. Okay, where f is a fermionic number. Now you may wonder, in a bosonic string theory, how can we get fermionic states? Okay. And these essentially come from the ghosts, right? Because when you actually carry out the analysis, you also have the Fourier-Popov of ghosts, and that's what is responsible for this. Okay. And we'll see later the effect of this, okay, and more precisely how it comes. So this I'll write as integral 0 to infinity dt over 2t, then sum over I e to the power minus 2 pi t times HIB. These are the L0 eigenvalues of the bosonic open string modes. Okay, so this is open string partition function, right? Because on the D-instanton is open strings that are propagating. So this loop essentially is a loop of open strings. So these are open string spectrum on the D-instanton. So minus sum over j to the minus 2 pi t h j f. And I should also say that this trace over here, this trace, this includes a projection, by B0 C0. This is basically because the ghosts have zero modes, okay, and when you try to define the annulus amplitude, you have to soak up the zero modes by inserting the zero mode factors B0 C0. Okay, and this also comes naturally from the perspective of string field theory. Okay? But this is the projection you have to use, and this essentially means that we sum over states satisfying B0 on the state equal to 0. This is sometimes called the Siegel gauge condition from the string field theory perspective, but for us, it's just enough to know that the projection by B0 C0 essentially says that you sum over only those states which are analyzed by B0. So these are the zero modes of the ghost fields, okay, the worldsheet ghosts. And again, we'll see in more detail the definitions of these later. But let's now try to examine this a little more carefully. So we have this expression integral 0 to infinity dt over 2t. Now, the divergences that we had mentioned earlier, so these divergences come from diverges for HIB less than or equal to 0 or HJF less than or equal to 0 as t goes to infinity. Okay? That's where the sources of divergences are. Now, you may ask, what about t goes to 0? This, in fact, is what is known as the closed string channel divergence. And what one can show is that if in absence of closed string tachyons, and that is the case here, in absence of closed string tachyons, this term inside the square bracket actually goes to 0 as t goes to 0. And this means basically that there are equal number of bosonic and fermionic modes. And this whole analysis makes sense only when closed string tachyons are absent, right? Because otherwise you don't even know how to define the theory. So in all sensible theories where you are going to do this analysis, there will be no divergence from the t goes to 0 end. And we have seen this in our specific example in the specific context that we'll be dealing with, two-dimensional string theory. This is e to the 2 pi t minus 1, right? And this clearly goes to 0 as t goes to 0. So you only have to worry about divergences for large, for HIB less than or equal to 0 and HJF less than or equal to 0. And those come from the t goes to infinity end. So now let me write down the expression for A again. So A so the way we are going to analyze this is to pretend that these are positive, where of course these are this is well defined. Manipulate this expression and then try to make sense of that expression when these become negative. So when these are positive, okay, you can actually do these integrals explicitly because there's a finite integral. Sorry, this is the minus sign. I forgot. Because these are finite integrals. I hope I wrote the minus sign in the previous one, right? Yeah. So when these are positive, we have finite integral, and we can do this explicitly. And the result, okay, this half comes from this 1 over 2. The result is log of product over J, HJF, over product over I, HIB. Okay, this we can explicitly check by doing these integrals in this case. So then this means that e to the A, okay, which is what you are interested in. is given by square root of this product. And now for reasons that will become clear later, I'm going to write this as an integral, keeping track of all the normalizations, okay, because that's what we're after all. So you have dbi over square root of 2 pi. I'll explain what this prime is. So this prime basically means it's this product is over half the number that is here, because what I have done is to use the fact that for the fermionic states, these eigenvalues always come in pairs. Okay, and we'll see examples later, but it's a fact that at least in bosonic string theory, these always come in pairs. So I have written this as a sum over pairs, okay, product over pairs, okay, and dfj df tilde j. So this is half the number that appears in this product. And we have written this explicitly at hfj fj tilde fj. So when you do these integrals, you bring down factors of hfj, but only half of those factors. That's why the square root of hfj here. I should have put this square root. This is the whole square root over the whole thing. It goes all the way around. And then the bosonic integrals just produces 1 over square root of HIP. So this is the identity for positive values of this. So what we are going to do is to take this as a definition of e to the a. We take this as a definition of e to the a. Now, this of course doesn't help very much at this stage, because if HIB is less than or equal to 0, right, then again the B integrals start diverging. If HFJ is equal to 0, then the fermionic integrals start diverging and so on. So it doesn't help very much, but let's do it anyway. Because we will see that once we interpret it in this way, okay, there is a way to make sense of it. So the strategy that we'll be following is the following, as follows. So the strategy. So the first step will be to interpret this as a gauge fixed version path integral of gauge invariant open string field theory. Now here I should say that this open string field theory is a little, somewhat a big word, okay, because the open strings actually carry no continuous momentum. Because you are on a D-instanton. So what we have is really a zero-dimensional field theory. And what we call path integral is really an ordinary integral over a discrete set of variables. Okay. So you see this from here. Okay. You really have an integral over a discrete set of variables, okay, to make sense of this. Okay. Because these h's, okay, take only discrete values. There is a continuous index like the momentum. Right? Whereas on higher dimensional D-blends, okay, the h will contain a factor of k squared, which can vary continuously. Okay, but that's not the case here. So for what you are calling field theory, okay, it's a general word that we use, but it's really a zero-dimensional field theory, okay, ordinary integral. So this will be the first step. Then the second step will be to show that the HJF equal to 0 state. Now I'm calling modes, not fields, because they are really zero-dimensional fields. These modes arise from the breakdown of the gauge choice. This is specific to bosonic string theory, and for fermions, not all the fermionic zero modes are from the breakdown of the gauge choice. But in the bosonic theory, as we discussed, the fermionic states really come from the ghosts. And HJF equal to 0 basically means, you can see here, the HJF equal to 0 basically means that the ghost kinetic term is acquiring zeros. Right? Ghost kinetic term vanishes. So that means the further proof of determinant is vanishing. Okay? And that's a clear signal that you have chosen the wrong gauge. Okay? Because if you have chosen the correct gauge, then the further proof of determinant should have been non-zero. So just from that perspective, we can already see that the HJF, that if all this is true, then these must correspond to breakdown of the gauge choice. Okay? And we will see this more explicitly. Then we will show that the HJB equal to 0 modes arise from collective coordinates. So collective coordinates include, for example, the freedom of moving the D-instanton. Okay, in this two-dimensional string theory, there will be only one collective coordinate, and that corresponds to the freedom of moving the D-instanton along the time direction. So then, okay, so this, okay, we'll first let me identify the what we will show, and then how we'll get around the problems. And so finally, for the HIB less than 0 modes, okay, there will be no mode with this is, I have been calling this index I. So for HIB less than 0 modes, we can use the steepest descent control. To do the integral. But this needs to be justified. Okay? I mean, why you should integrate over the steepest descent control. So this we will see. So this need to be justified. So the idea is that once you have established that the fermionic zero modes come from the breakdown of the gauge choice, what you are going to do is to forget about the particular gauge choice that we have made and go back to the original gauge invariant path integral. Right? And if the fermionic zero modes are really coming from the breakdown of the gauge choice, then at least in the original gauge invariant path integral, these problems shouldn't be there. So we rewrite this in terms of the original gauge invariant path integral. And then we treat the collective modes appropriately so that they are integration over the collective modes, reproduce the energy conserving delta function. And then these modes we treat by the steepest descent. So that's the general strategy that we'll be following. And we'll see at the end that by doing this, we'll get a finite answer.
I have a question.
Yes, go ahead, please.
Yeah, clearly number 2 has, I can see the problem. The number 3, does it mean that it has some problem or like a collective coordinate or what?
No, it doesn't really have a problem, right? That in the normalization, so this basically says the normalization, that whatever path integral gets into the normalization, right? The integrand is independent of the collective coordinate, which is good because that basically shows that the integrand doesn't depend on where you place the D-instanton. But some things depend on the collective coordinate, and this integral has to be done at the very end, right? So once you have made this identification, then you know that this collective mode integral has to be done at the very end. So what's going to happen eventually is that you'll get an integral, like integral, let's call it dy, if y is the collective, maybe y I have to use for something else, let me use, say d chi, okay, where chi is the collective mode, describing the position of the D-instanton. And then once you insert the closed strings, right, that like this amplitude, you'll get something like integral I omega I times chi. The normalization factor doesn't have any chi dependence. Okay, that's what is reflecting the fact that it's a zero mode. But eventually you'll get an integral like this, and this will produce a 2 pi delta omega I. It's not a problem, it's in fact needed, the collective mode is needed to recover the energy conserving delta function. Okay, because as we discussed, that individual, these diagrams do not have the energy conserving delta function. Is that point clear?
Yes, yes, thank you.
Now it turns out that here the situation is even simpler for 2D string theory. For the 2D string theory, remember the expression for A, which was integral 0 to infinity dt over 2t e to the 2 pi t minus 1. And if you compare that with the general expression, integral 0 to infinity dt over 2t trace of e to the minus 2 pi t L0 times minus 1 to the f. We see by comparing these that contribution from L0 greater than or equal L0 greater than 0 modes, which will give negative power of e to the 2 pi t, modes all cancel. Basically means that there are equal number of bosonic and fermionic modes with L0 less than positive. So those modes all cancel. So this means that we don't even have to integrate over them. We can just drop them from the integral.
You mean L0 bigger than 0 or L0 less than 0?
No, L0 bigger than 0. Because it's e to the minus 2 pi t L0, right?
Yeah.
So L0 bigger than 0 will give e to the minus 2 pi t parts of e to the minus 2 pi t. And this has only positive power of e to the 2 pi t, right?
Mm-hmm.
So all the positive L0 modes just cancel, right? They're equal, they pair between bosons and fermions.
But you're making an analogy with the tachyon on the...
No, I'm just, this is the specific case of two-dimensional string theory, right? And this is the general result in all bosonic string theories, right? In all string theories.
And the
just
tachyon in the...
right? And you see that
I see what you mean. Sorry. Yes, now I understand.
Because
There's only a
positive L0
contribution.
negative parts, right?
I see. I see. Thank you.
And those are just not there. Is that point clear?
Yes, thank you.
So we can drop integration over L0 greater than 0 modes altogether. Okay. And in fact, this simplification also happens for superstring theories. Okay, if the critical superstring theory, when you try to do a similar analysis, you do find that again the positive L0 modes cancel. They are the cancellations between the Nebel-Schwarz and Ramon sector. Here it's between the matter sector and the Gauss sector. Okay. So let's just list the negative L0 modes, okay, in this theory and see if we get this result. Okay, and it will be useful also later. So we want to list all the L0 less than or equal to 0 states in 2D string theory. I should have
Ashok,
more. Yes, go ahead, please.
So you said the L0 when L0 is positive, you mean one can confirm that result, or do we just guess it?
No, just by because this came after all from the calculation, right?
Yes.
Of the annular partition part. So if you compare it with this,
yes,
we can check that they cancel, right? But if you want to do it more explicitly, yes, indeed, you can confirm this.
I see. Okay.
List out all the states, and you will find that there is exact cancellation between the bosonic and fermionic modes.
You mean fermion case? It means ghost. In
Exactly.
This case, like a bosonic thing. Okay.
Exactly.
Okay. Thank you.
But just by the fact that the annulus partition function is given by this, in fact, annulus partition function captures the information about the spectrum, right? Because it is by definition, this came actually by calculating this in two-dimensional string theory, right? This was a BRY result, but the way they got it is by calculating the strings. So just by comparison, we can see that all the L0 positive states have cancelled. Yes. Is that clear? Okay, so let me list the L0 negative states and then see that we agree with whatever results BRY had given. So I should have made this more clearly. What you are listing is not the L0 less than or equal to 0 states in two-dimensional string theory. I should have said that these are open string states. On the D-instanton of two-dimensional string theory. Up to this, okay? That's what you are listing. So for this, I have to now introduce the oscillator modes. Okay, and since you have to do this anyway, this is a good time to do this. So we define the oscillators as follows. Okay, so these are the standard mode expansion. This √2 is basically because in the alpha prime equal to 1, so I'm using the alpha prime equal to 1 unit. There the del x operator product has a half, right? So to normalize it properly, I have this in fact minus half. So to normalize it properly, I have multiplied by I √2. So this is Z is here. And then the standard expansion for C and B, CZ is sum over n C and Z to be minus n plus 1. Okay, this reflects that the C has dimension -1. BZ is sum over n B and Z to the power minus n minus 2. So B has dimension 2. And for the Liouville part, we don't need the full Liouville part. In fact, we only need the energy momentum tensor of the Liouville part. So TL of Z as sum over n L n Z to the power minus n minus 2. And the reason that we don't need the explicit Liouville part is because the spectrum of open strings essentially contains the primary of the vacuum of the Liouville and modes of TL acting on the vacuum. Okay, that's all. Those are all the Liouville sector open strings that we have on the D-instanton. So this SL2R invariant vacuum, that SL2R invariant vacuum, so this satisfies the standard relation. So alpha n acting on the vacuum is 0 for n greater than or equal to 0. Then Cn acting on the vacuum is 0 for n greater than or equal to 2. So, and all these follow just from the demanding that the C0, del x0, all these should be regular at z equal to 0. Okay, that's where these numbers come from. So for n equal to 2, for example, there is a z inverse, right? So C2 better annihilate the vacuum, otherwise there will be singularity, Cz. Bn acting on the vacuum is 0 for n greater than or equal to minus 1. And finally, the LLN acting on the vacuum is equal to 0 for n greater than or equal to minus 1. This is a standard relation in two-dimensional safety. So based on this, we can now try to build states, and we'll list out all states with L0 less than or equal to 0. So states with L0 less than or equal to 0 is total L0. We have this C1 on 0, then C1 alpha minus 1 on 0, and then the vacuum itself, and C1 C minus 1 on the vacuum. You can check that these are the only states in the Siegel gauge, and I should list some other states. Let me list them here. That is by applying C0 on each of these. So these I have listed separately because in the original expression, okay, when you are taking the trace over the open string states, I said that you should include only the states that are annotated by B0, and these are the ones which are satisfied. Okay, so these satisfy B0 on state equal to 0. Okay, these don't. Okay, so we should really include these states in the trace. So let me list the L0 eigenvalues. So this is L0 equal to minus 1, so both of these. And these are all L0 equal to 0. This is L0 equal to 0. All of these, in fact. Okay, so one set of states with L0 equal to minus 1, the others with L0 equal to 0. And now we have to say which are bosonic states and which are fermionic states. And it turns out that the bosonic states, okay, whether it's a boson or fermion, is oppositely correlated with the Gauss number. So let me mark them here. So these are bosonic states. These are B. And these ones are fermionic states. So you have two bosonic states and two fermionic states. So let's check if it matches with the result that we had. So trace of e to the minus 2 pi t L0 minus 1 to the f you see, this is a bosonic state with L0 equal to -1, so that gives you e to the 2 pi t. This is a bosonic state with L0 equal to 0, so +1. And these are a pair of fermionic states with L0 equal to 0, so -2. And that's exactly e to the 2 pi t minus 1. Okay, so that's what explains how we got this e to the 2 pi t minus 1 in the first place. Okay, this is basically coming from the bosonic states give positive contribution, fermionic state gives negative contribution.
What if you define opposite in opposite way? So of course it does not give the result, but don't we have any freedom to?
Not really, because the point is that this, for example, is a tachyon, the open string tachyon. That's clearly bosonic. This one is a collective mode. Okay, this is what translates the mode along the x direction. Right? So those we know are bosonic modes. So that already fixes how to correlate. And this is, I mean, from the worldsheet language, this is the difference between what is called the integrated vertex operator versus the unintegrated vertex operator. Right? Normally in a bosonic string theory, right, and we start with if energy on amplitudes. Right? We fix 3 vertex operators, right, and integrate over one. Right? The one we integrate over doesn't have any C attached to it, but the ones we fix has a C attached to it. Right? That's how we define the worldsheet amplitudes. So these states, right, are the corresponding vertex operators are what we call the unintegrated vertex operators. Okay, that's why they have this C. So you have to strip off the C to see if they are bosonic or fermionic, right? Once you strip off the C, you can easily see that these represent bosonic modes. So here you really don't have any choice. Okay, the way string theory works is that you assign bosonic statistics to these and the fermionic statistics to these. Is that point clear?
Yes, clear. Yeah, thank you.
So once you get the vertex operator by stripping off the C's, right, then it becomes clear this is like the Del X, right? That's the translation mode of the instanton along the X direction. And that clearly is a bosonic mode. Right? It cannot be a fermionic mode. Okay, so let me remind you what we want to achieve, right? We have this integral over there, or a path integral. Yeah, so you have an integral like this. And we want to interpret this as a gauge fixed version of some gauge invariant path integral. Okay, gauge invariant open string theory path integral. So for this, you have to now introduce something about open string field theory. Okay, a little more detail than what you have seen so far. But fortunately, we don't still need much detail. So introduction to open string field theory. And in fact, we will only need the quadratic part of the action of open string field theory. So it's not that hard. So for this, we first assign Bose number, to worldsheet fields. And the way we assign it is that we assign C and C bar have Bose number 1. B and B bar have Bose number -1. And matter, that means X and Liouville, they have Bose number 0. And the vacuum also has Bose number 0. The SL2R invariant vacuum has Bose number 0. Okay, once you specify this, then you can determine the Bose numbers of everything. So let's suppose that we introduce phi nr as a basis states of Bose number n. And indeed, for L0 equal to 0 states, we can do it explicitly. So let me do this because that's what we'll need. For L0 less than or equal to 0 states, we have a finite list, right? So you can easily have a finite list. So let's try to do this. So n equal to 0. Okay, the only state here is a vacuum. For n equal to 1, there are several. N equal to 1, we have the C1 on vacuum, the tachyon. Then C1 alpha minus 1 on the vacuum. And then you also have the C0 on vacuum. Right? These are all host number 1. Then you have n equal to 2. N equal to 2, we basically multiply by C0, many of them. Okay, but first, C1, C minus 1 on 0. So I'm writing the Siegel gauge ones first and then the out of Siegel gauge ones. Then C0, C1 on 0. And C0, C1 alpha minus 1 on 0. And finally, for n equal to 3, I have C0, C0, C1, C minus 1 on 0. Right? So everything can be done explicitly, and that's what we need. So far, I have not said anything about string field theory. Right? This is just a worksheet. Okay, now we are going to introduce the string field. So the classical open string field is a state psi of host number 1. State psi, maybe I should say, of host number 1 in the worksheet theory. Now, let's elaborate on what it means. So what it means is the following, that given an arbitrary state of host number 1 in the worldsheet theory, I can expand it out. I can write this as sum over R, psi R, phi 1 R. And these coefficients of expansion, so this is the basis state, and these are the dynamical modes, dynamical degrees of freedom. These are the dynamical degrees of freedom in the open string field theory. So which means that the path integral is to be done over these modes. Okay, times whatever else you have. So this is what one means. So these are the modes of what you have to integrate. And you can see that these will be finite in number in the present case, because for host number 1, we counted, right? There are 3 such states, so there will be 3 modes to integrate. Okay, so everything can be written down explicitly. Maybe I should write it here anyway. Okay, so I can expand.
I think connection is bad.
Ashok, you are muted.
Yeah, can you hear me now?
Yes. Yes. Can you share the screen again? Yeah.
Yes, I'll do that because our internet failed, so I am now connecting through my mobile. I'll try it once more. Is it okay?
Yes. Okay.
Okay, thank you. Let's hope that it works. So, yeah, here I was going to write the expression for psi. So psi will expand as psi 0 on C1 on vacuum plus psi 1 on C0 on vacuum plus phi on C1 alpha minus 1 on vacuum. Okay, so these are the modes you have for which you have to do a path integral. So the action S is given as half psi QB psi plus interactions, okay, which you will not need, as I said, not for this lecture. So you can substitute the expansion of psi and write this as some half sum over RS phi 1 R QB phi 2S psi R psi S. So here QB, I should have said, QB is the worldsheet, the BRST operator. QB is a BRST operator on the worldsheet. So this has some definite expression, so you can calculate this, and you get this action as a function of the psi r's. Okay, and that's what one means by action, right? It's a function of the dynamical degrees of freedom. So this theory also has a gauge invariance. So the theory has gauge invariance. As gauge invariance. And a gauge transformation parameter theta is a state of host number 0. What this means is the following. Okay, what this means is that if we expand theta as a sum over u, theta u times phi 0 u, okay, expand in the basis of 0 host number states, then these are the gauge transformation parameters. So these are the transformation parameters.
Could you specify the ghost number of a BRST operator and the bra state?
Yes, and this has ghost number 1. This has ghost number 1.
So bra has the same ghost number?
Yes, bra has the same ghost number. So total ghost number adds up to 3. And that's exactly what you need to get a non-zero matrix element, right? In open string theory, because there is a anomaly in the ghost number current. For example, in a 3-point function, requires 3 fixed vertex operators, right? Because on a upper up plane, you can, for example, fix 3 points on the boundary, okay, where you insert the open string vertex operators. And because these are not being integrated, you have to accompany each of these by the C. So you have 3 C's whose matrix element is non-zero. And that's essentially because on a upper up plane or on a disk, the total ghost number non-conservation is given by 3. Is it the
reason why you choose a ghost number 1 field as like a dynamical field?
In a sense, yes. But also, I mean, these should contain the physical states that you're familiar with, right? And those are ghost number 1. The fixed vertex operators, the physical vertex operators which are unintegrated, they do have ghost number 1. So it better be the dynamical fields include the ones that we call physical fields, right? Like the transition mode of the D-instanton or the tachyon and so on. And this feature is true in general. It's not specific to D-instantons, right? On all D-branes, this is the feature. That you have to choose ghost number 1 states as the physical open string states, and this is the structure of the kinetic operator.
Okay.
Okay, so this is not specific to D-instanton. This is general. Okay, so let me now give the gauge transformation parameter, gauge transformation law. So the infinitesimal gauge transformation law is delta psi is QB theta plus nonlinear terms, right? Order psi theta terms, nonlinear terms, which will not need. For us, the linearized part is enough. What this means is the following, okay? That if you expand this out in a basis, delta psi r times phi 1 r is sum over u theta u QB times phi 0 r, phi 0 u. So to find the transformation of delta psi r, all you have to do is that you have to expand this as linear combination of the phi 1 r's, because this has ghost number 1, and read out the relationship between delta psi r and delta theta. Okay. So this gives delta psi r as function of theta. That's what I mean by this is the gauge transformation. So in the present case, for L0 less than or equal to 0 states in 2D string theory, on the instanton, again, all of these are happening on the D-instanton. On the D-instanton in 2D string theory, if you remember that list, there is really only one state of ghost number 0, and that's a vacuum. So their theta is equal to just theta on vacuum. That's the only thing that we have. So basically, you have only one parameter, one gauge transformation parameter. Okay, so now let's define, this is just a definition, a gauge invariant partition function. Okay, we'll see why this definition is useful. Gauge invariant partition function. And that I'll take to be the following. The standard definition that one uses, d psi r product, sorry, the product over here, product over r d psi r e to the minus s divided by integral product over u d theta u. So we integrate over the all the modes of the gauge invariant theory weighted by to the minus s and divide by the volume of the gauge. Right? That's the standard definition of a partition function. This normalization is completely arbitrary. Okay, this is arbitrary at this stage. Okay? Final result will not depend on how you choose this normalization. Now, suppose you take this and naively gauge fix. So we now suppose we naively gauge fix to Siegel gauge. B0 psi equal to 0. Okay, this is what is normally called the Siegel gauge. Now, what does it mean exactly? Okay, that means that we take this expansion sum over R, psi R, B0 on phi 1 R, okay, set is equal to 0. Okay. Now, some of these basis states will automatically be annihilated by B0, so their psi R's remain. Okay. There are other basis states for which this is non-zero, and those psi R's are set to 0. Okay. So, in the 2D theory, okay, let me give. So, this expansion, okay, you remember that you had psi 0 on the vacuum, on C, sorry, psi 0 C1 on vacuum, plus psi 1 C0 on vacuum, and phi C1 alpha minus 1 on vacuum. So the Siegel gauge will correspond to setting this equal to 0. Okay, that's the meaning of Siegel gauge choice. Okay, so psi 0 and phi will survive, this will be set to 0. Now, this I'll not do explicitly, but let me just make a statement. I'll motivate how this comes. Okay. So if we do the gauge fixing by standard Fourier-Popov method, if we use the standard Fourier-Popov method, we get this gauge invariant path integral becomes integral product over I dBi, okay, something that we had seen earlier, product over j dfj df tilde j exponential minus half Okay. So let me just explain how this comes, okay, without actually going to the calculation, because the calculation is more or less straightforward. Okay. So this one is essentially the gauge fixed version of the gauge of the kinetic term. Okay. So what happens is, so here you see the sum over I now runs over only the Siegel gauge fixed fields, right? So in the previous notation, the sum over I will run over only two values, this one and this one, okay, because this has been set to 0 in the Siegel gauge. Furthermore, one can show that when sandwiched between Siegel gauge states, QB basically reduces to C0 L0. Okay. There are other terms in QB, but those don't contribute when you sandwich them between Siegel gauge states. Okay. And so because of this L0, this gives the HIB. It picks up the L0 eigenvalue of these modes, right? So that's where this HIB comes from. These ones are the Fourier-Popov ghosts. So what is a Fourier-Popov ghost kinetic operator, right? If you formally, it should be like delta of the gauge fixing term, right? That is B0 psi over delta of theta, right? This is formally, you can write in terms of components, right? I am just writing it as a formal expression, but it's actually delta of the gauge fixed component of psi, okay, and derivative with respect to the appropriate component of theta. Here, of course, there is only one such theta, but this has to be expressed in terms of theta, and for this you use the fact that the transformation of psi is the QB on theta, right? So this is like delta of B0 QB on theta over delta of theta, and B0 QB acting on the single gauge states, in fact, is just L0 again. That's how you get the L0 in the Faddeev-Popov ghost kinetic term, and that's what explains these H's. But if one can do this more explicitly by writing in terms of components, and this is what one arrives at. And now you may recognize this as something that you have seen before. So what is this? This object is almost this e to the a that he wrote down, except that there is a 2 pi to the nb by 2 times e to the a, because in the expression for e to the a, we had dbi over square root of 2 pi. Here you don't have. Okay, here you don't have because I have just chosen to start with the normalization where you don't have. But that's just that will not make a difference at the end. And NB here is the number of bosonic modes in the single gauge. Right? That's what this product is running over. So what is the strategy now? Strategy is that we are going to write e to the a as I over 2 pi to the nb by 2. So let me do that and then I may come back to this. So you are going to write e to the a as I over 2 pi to the nb by 2. And take this as a definition, as the definition of e to the a. Now, if you look at this, you can clearly now see that the problem that we face with HF equal to 0, right? These are what? HF equal to 0 is basically this determinant, coming from this determinant, right? This is the B0 QB gives the L0. So vanishing of H means that the Faddeev-Popov the ghost kinetic operator is acquiring 0 eigenvalues. And a ghost kinetic operator acquiring 0 eigenvalues is a clear signal that the gauge choice is breaking down. Because the Faddeev-Popov determinant vanishes. So the idea is that this is ill-defined because there is a ghost, the Faddeev-Popov determinant is becoming 0. So we'll use this formal equality between this and this one to write e to the a in terms of this original gauge invariant path integral. So we'll write e to the a as 1 over 2 pi to the nb by 2 times integral product over r d psi r e to the minus s over integral product over u d theta. And we will see that this integral now can be made sense of. Okay, are there questions?
Why in this way you have no like ambiguity in normalization? Is it correct?
You don't have any ambiguity, no.
Okay.
You see, because okay, let me emphasize that again. That suppose I had put a constant here, right? Suppose I had put a constant here. That constant will be here also. So this will be e to the this times e to the a times that constant. So when you write e to the a in terms of I, that constant will simply cancel, right? Because I has that same constant. So this expression has no ambiguity.
Okay.
Okay, so that's why I said that constant was just a matter of definition, right? It's just showing the equality of two things. And that's what you're using to write the e to the a as this thing. Is that point clear?
Yes.
NB is infinite though, like.
No. NB in this case is is the number of single gauge fixed states, right? And we are already restricted to L0 less than or equal to 0.
Only those of L0.
Exactly.
Only, okay.
So NB is 2, in fact, in this case. Okay, let me write the expression. So in the present case, at present, the full string field is psi 0, C1 on 0. Okay, by now, I think you have seen it enough times. Psi 0, C0 on 0, phi 1, and then phi C1 alpha minus 1 on 0. Okay. So this single gauge state is this and this, right? So these are the single gauge states. So these are single gauge states. So NB is 2. So NB is 2 here. This integral, of course, runs over everything. Okay, so this is got 3 integrals, 3 variables, because this is gauge invariant path integral, right? That runs over psi 0, psi 1, and phi. This is theta, just one single integral. And S you can calculate. So let me write down the result for S. So S, which is half psi QB psi. If you substitute this, you can show with some after some algebra that this is minus half psi 0 square minus psi 1 square. Okay, so you are going to now substitute him into this and gets the expression for e to the a.
But in principle, the original in string field theory, you have an infinite number of fields, but you know that they're not going to contribute, so you're restricting the integral over the modes that you're interested in.
Exactly, because those we have seen cancel anyway, right? So for L0 larger than 0 states, there is no problem with single gauge. So there the single gauge fixed path integral is the same as the gauge invariant path integral. And in the single gauge fixed path integral, it's clear that they all cancel, right? Because they don't contribute to this e to the a.
Very good. Thank you.
Okay, so the integral that we arrive at the end is this one. So e to the a is 1 over 2 pi times integral d psi 0, d psi 1, d phi e to the power minus a. So that gives you half psi 0 square plus psi 1 square divided by integral d theta. Okay. So now the idea is that we are going to do, the psi 0 and psi 1 integral along the steepest descent contours. This will be justified later. But for now, let's just note that because these are positive, okay, these are along the imaginary axis. Okay, so we just rotate the contour to the imaginary axis. And what we get is 1 over 2 pi times minus 1. Okay, this is minus 1 is a square of I square basically, because each contour rotation gives a factor of I. Okay, and then a factor of root 2 pi. Okay, so psi 0 gives you square root of 2 pi and psi 1 gives you square root of pi. So that's square root of 2 times pi. And then you are left with integral d psi 0, integral d phi over integral d theta. So that's what, minus 1 over root 2 integral d phi times integral d theta. So you have to now make sense of these integrals. So let me now say how to do this phi and theta integral. Okay. So phi, what is phi? So the phi is a coefficient of the C1 alpha minus 1 vacuum, right, in the expansion. Expansion of psi. And this, in fact, is the vortex operator of the translation mode of the D-instanton. Okay. So this is clearly related to the D-instanton position. D-instanton position phi tilde along psi, along x. Okay. So what you mean by related? That means that giving a vacuum expansion value to phi means that phi tilde has been shifted by something proportional to phi. But the proportionality constant is important. Okay. So to find the precise relation, the way we proceed is as follows. Okay. We first note that if we have, say, closed string on the disk, okay, how many doesn't matter, something like this, say. Then the phi tilde dependence should be proportional to e to the minus I omega phi tilde. Okay. Where omega is the total energy. Okay. This simply follows from the standard fact that if phi tilde is a position along the time direction, right, and if omega is the energy carried by all the closed strings, so the open strings don't carry any energy, right, but closed strings do. So if the closed strings carry some amount of energy omega, then because this is a position along x, there is a standard e to the minus I omega phi tilde factor that must accompany any amplitude. So this e to the minus I omega phi tilde we can expand out. E to the minus I omega phi tilde we write as 1 minus I omega phi tilde plus etc. Why we did this, it will become clear in a minute. So we now compare this with an amplitude where you have the same closed string insertions, but you are not going to shift the D-instanton, okay, by phi tilde. We are going to insert a phi vortex operator. Okay, that corresponds to inserting a phi in this amplitude. So the phi vortex operator, we know it's a I root 2 del x. Okay, this is the integrated vortex operator. So you basically get integral dz times I root 2 del x of z together with the various these vortex operators, okay, which will carry this into the I omega I xi factors. So you can carry out this by your operator expansion, right? Del x z to minus I omega I xi. This can be some at z i's. You will get 1 over z minus zi factor. You close the contour, pick up residues, okay. And what you can show that this will be proportional. Okay. And then there's a coupling constant, okay, because these are open strings, so it will be accompanied by an open string coupling constant. So this will be proportional to some GO times the total energy times some omega I times the original amplitude, okay, product over I to the I omega I x of zi. And now the idea is that we compare this coefficient over here, okay, this is omega, with this coefficient, right? If phi tilde is inserted, you expect a factor of minus I omega. If phi is inserted, you can pick up exactly what factor you insert, okay, what factor you get by doing this calculation, and you compare. And using this comparison, we can find the precise relation between phi and phi tilde. Okay. So I'll not do the calculation explicitly, but let me write the result of this calculation. So the result of this comparison it basically requires keeping track of the factors of 2 pi and root 2 and so on, right? Because OPs have various factors of 2. But what to find at the end is that phi is related to phi tilde by phi tilde over pi root 2 times geo. Okay, geo comes because geo accompanies phi, right? Here there is no phi tilde. Pi also, you can see this control integral will give a factor of 2 pi I. Okay, that's what gives this pi. I, of course, is matching. The omega matches here, right? And then there's a root 2, right? This root 2 is responsible, and the OP has a half. So by putting all those factors, you get this relation. Are there questions on this? Okay, now theta. Okay, we have to also understand what is theta. So theta accompanies zero, right? So the gauge transformation parameter is theta on 0. So using this and known nonlinear gauge transformation properties in open string field theory, of open SFT, we can find the gauge transformation under theta. Okay, take any state and you can figure out how it transforms under theta. So now we have to compare this. So we compare this with the following gauge transformation. With rigid U1 gauge transformation on the D-instanton. So as you know, every D-brane has a U1 gauge symmetry living on it. So what does the U1 gauge symmetry do? Right? If you have a D-brane here, and if you bring another D-brane, let's call this a spectator D-brane nearby, then an open string that stretches between these is charged under the U1. Okay, that's the standard U1 that lives on all D-branes. Okay. So if you denote by theta tilde the parameter of this transformation, the rigid U1 transformation, then this open string state will pick up a phase of e to the I theta tilde, which you can write as 1 plus I theta tilde and so on, multiplying the same state. Okay, it's just an overall phase that multiplies the state. So you know how the open string modes transform under this rigid U1 symmetry. On the other hand, by using the gauge transformation laws of string field theory, you know how the open string modes transform under theta. And then we compare. So the principle here is that we compare the open string gauge transformation generated by theta with the rigid U1 transformation U1 generated by theta tilde. And this gives, okay, again, I'll just write down the result. This gives a relation as theta is equal to I theta tilde over G0, the open string count. Again, this is straightforward calculation, just comparing an amplitude in open string theory with this simple gauge transformation law that we see here. Okay, just multiplication by I theta tilde. Infinitesimal transformation. Okay, so now we are almost there. So e to the a was minus 1 over root 2 times integral d phi over integral d theta. Okay, now the idea is that we'll write phi in terms of phi tilde, theta in terms of theta tilde. So that's minus 1 over root 2 times 1 over pi root 2 times GO. This came from writing phi in terms of phi tilde. And now theta has to be written in terms of theta tilde. So that gives you G0 over I, okay, because it's in the denominator. Then you get integral d phi tilde over integral d theta tilde. This one is easy. This is 2 pi. Okay, why is this 2 pi? Because the way you have normalized theta tilde, it just picks up this phase, right? So theta tilde clearly has period 2 pi. So theta tilde integral gives you 2 pi. And what about this? So integral d phi tilde, of course, has to be done at the end, okay, after you have computed the whole amplitude, not just the exponential of the annulus, but after you put in all the disk factors, etc. At the end, you do this integral over the bosonic zero mode, the collective mode. And this simply generates the energy conserving delta function 2 pi times delta omega, right? Because the way I normalize phi tilde is by demanding that the coupling of phi tilde has this structure. So the phi tilde integral will just give the delta 2 pi delta omega. Okay. So this is not normally counted as part of e to the a, right? This was written separately. If you remember the lecture in the first lecture, okay, this is written separately. Not as part of e to the a. So as far as e to the a is concerned, it's just this part with theta tilde, it is being equal to 2 pi. And this you can recognize, this whole expression you can recognize as, so minus 1 over 4 pi square, right? I over 4 pi square, minus an I. This gives you I over 4 pi square. Now, unfortunately, we are not done yet. I have 2 minutes. Let me just say a few words, and maybe next time we'll try to do this in more detail. So what remains to be done? We have to understand if the steepest descent contour is the right one to choose. Now, for psi 0, you remember we have to use for both psi 0 and psi 1. For psi 1, it's trivial. For psi 1, it is straightforward. And the reason is that when you actually carry out the expansion of the string field, what one finds is that the real string field actually corresponds to imaginary psi 1. So the fact that we have integrated psi 1 along the imaginary axis, okay, is actually good, because that means that we are actually integrating the string field along the real axis. So for psi 1, there is no issue. Okay, steepest descent contour clearly is the right one. So we'll argue that for psi 0, the tachyon, we actually should integrate over half of the steepest descent contour. In other words, that instead of taking this minus I infinity to I infinity, d psi naught e to the half psi 0 square, we should actually do the integral. Okay? This is not the correct one. The actual integral is minus I infinity to 0 d psi naught e to the half psi 0 square. So this will produce an extra factor of half. Why this is the case, we'll discuss tomorrow. But let's just take this extra factor of half for now and let's see what we get. So if we include this extra factor of half, then remember that n was taken to be I e to the a. So that gives you I e to the a, as we have found earlier, was I over 4 pi square. Okay, that was by integrating over the full steepest descent contour. You have here I over 4 pi square. And then with this extra factor of half, we put a half, that's minus 1 over 8 pi square, which is exactly the matrix model result. What we find by comparison to matrix model. So today I'll stop here. Next time I'm going to say where this factor of half comes from, and then we'll go on to do other calculations. Are there questions?
Is there an interpretation for the so the in the x direction you have a zero mode, which is just translation on the x time direction, yeah. But there is no such neither zero mode nor negative mode on the Liouville direction. There is no, like, the position of the instanton is completely fixed there.
Completely fixed, exactly.
And where is it fixed? Like,
well, it's fixed in the strong coupling region, right? It's fixed somewhere in this region. If you draw the Liouville potential,
right?
It fixed somewhere here.
But that somewhere seems a bit.
Yeah. So the point, of course, you don't. Find the position of the instanton by looking at this picture, right? The way one finds the instanton is by writing down an appropriate boundary state that satisfies all the consistency conditions.
Right.
So it's done, by following bootstrap essentially, right? That you say that you have to have a boundary state whose inner product of itself should have the interpretation as an open string partition function.
Mm-hmm. And
then you put various consistency conditions, and that's how you find the spectrum on the open string, spectrum of open strings on the D-instanton.
I see.
But if you want to ask physically where it's fixed somewhere here, right? Of course, you don't. This is not the way we describe where it is fixed. Right? It's fixed somewhere in this region. But the way we describe it is by using the conformal bootstrap.
I see. And
just like many of the minimal models, right, are not described by writing a Lagrangian or writing a physical picture, but just by consistency of the correlation functions. Right? It's similar here.
Right. Yeah, and I should also not look at this picture because otherwise I would think there is going to probably be a negative mode or something moving in one or the other direction. But
yeah, so the negative mode, okay, or the D-instanton has a negative mode, right? That's the tachyon.
Yes.
And in fact, we will see this next time.
I will see this. Okay.
So this is an unstable mode, right? This is a saddle point of the path integral.
Mm-hmm. And the negative mode is related to motion in the Liouville direction?
No, not in an obvious way, right? But if you think in terms of the matrix model, right, then you can say that, okay, indeed the negative mode is related to motion in Liouville direction, but you don't see it from the string theory perspective.
Okay.
From the string theory perspective, D-instant, the tachyon is just a mode on the open string that can roll.
Right, like the typical open string bosonic deep range
Exactly.
tachyon.
That's right. Right? Which doesn't necessarily have a space-time interpretation.
Exactly. Okay.
Okay,
I
any
have
other-
a question. Yeah, I
ahead.
have a question. So I could understand why this delta function or energy conservation appear, but still there is some step which you change it from the integral over the phi tilde to the delta function. To me, it's still not clear. Yeah, that
Okay.
one. So to me, it just kind of jump. But could you explain a little bit more?
Just say this more clearly, right? It's almost here. Okay. So we define phi tilde so that phi tilde is a D-instanton position, so you expect a dependence like this. So this part is clear.
Yes.
This is just standard kinematics. Okay. Now we are saying
Okay.
that let's try to compare this with the coupling of phi to the same amplitude. Okay. Take a set of closed strings inserted here, and we put a phi vortex operator here.
Okay.
So the phi vortex operator is given by this I√2 partial x. So you insert that vortex operator and you integrate, okay, with an open string coupling. So now this operator expansion, the operator expansion of del x with del x with e to the I omega I x of zi is like it gives you minus I omega I times over z minus zi with a factor of 2. Okay, that's and then the same minus I omega I x.
Yes.
So you substitute this, and using that, this correlation function del x z with this can be written as say sum of this 1 over omega I over z minus zi times the original amplitude.
Yes.
Okay, so this the step that is missing here is that this is given by sum over I 1 over z minus zi, maybe a minus I omega by 2 times this product over I to the I minus I omega I x of z. And now this z integral we can do by contour integration, right? Because you are just doing z integral around this the center, the middle. So you just pick up we can evaluate this by residue theorem, right? We pick up the residues at z equal to zi, that gives you just a factor of 2 pi I. So you get 2 pi I times the total energy. This is omega I. So after you do the z integral, here there's this z integral over here, we get 2 pi I times sum over I omega.
Yes.
So that gives a coupling of phi to this.
Yes.
So let me write this. So the expected coupling of phi tilde. So you compare the coupling of phi tilde, which should give you minus I omega times the original amplitude. And the coupling of phi, which has a G open, then some 2 pi I, etc. And then the same minus I omega, same I omega because of this OP. Yeah, because of this factor over here. Yeah, so because of this factor over here, we get this times the same original amplitude. And now just compare. So this is I omega phi tilde. This is a phi you have inserted. So just compare this with this.
Uh-huh.
The I omegas cancel, right? And all we are left with is some factors of pi, etc., and some geo, right? And that gives this phi equal to phi tilde over g times, well, I don't remember whatever, g times square root of 2 pi or whatever, right? That's where it comes from.
Yeah, that part, that part is clear. But what I'm saying is later you said that you can get the delta function, but delta function of the omega. So that.
Oh yeah, okay. Yeah, so that the point is, so here coupling of phi tilde, so this is the leading order coupling, right?
Yes.
The total coupling is e minus I phi tilde times sum over I omega I.
Then okay, yeah.
So once you change variable from phi to phi tilde, the phi tilde dependent comes like this. Okay, and then you have the original amplitude. And now we can do the phi tilde integral. So the phi and phi tilde relation you get by this comparison, and after you have converted to phi tilde, then you know the actual dependence on phi tilde, the full dependence, right? The full nonlinear dependence, that's this. That's just from the fact that phi tilde is a D-instanton function. And then this integral d phi tilde will give you the delta function.
I see. Now I understand. Thank you.
Okay. Are there other questions? Okay. So if not, I'll stop here and then tomorrow we'll continue.